Our next award is actually ASLO's, well, actually until a week ago was ASLO's newest award, but in fact now it isn't ASLO's newest award, but it's one that we've only presented twice in the past. This is the John Martin Award for a high impact paper. This was established in 2005 to recognize a paper in the aquatic sciences that's judged to have had a very high impact on subsequent research in the field, and it's absolutely forbidden that it be written on the Crenarchaeota. I've learned to pronounce it now, though. The model for this paper was, of course, the Martin et al. Paper in 1991, which laid out the case for iron limitation of phytoplankton production in the ocean. And the award is to be given to a paper that's at least 10 years old and generally not more than 30 years old. The past recipients are listed there at the bottom. I'm delighted to announce that the paper receiving the award this year is the Eppley and Peterson paper on particulate organic matter flux and planktonic new production in the deep ocean, which was published in Nature in 1979. These are some just brief notes, and I promised Richard that I would skip over this figure because he's using that one too. But it's built on this paper was built on the new production concept of Dugdale and Goering, and it extended that approach in a way that showed us many things that we didn't know before, and the data of the time, which were very sparse, suggested that the proportion of new production depends on total production in a very predictable sort of way. It was a broad view, a paper with a very broad view that addressed a variety of different issues that are listed there, and I think Richard will be talking about that in a minute. Also, many things have happened since then, but the findings of the paper and the ideas in the paper have been the new production paradigm has been robust, and all these new sorts of observations have been incorporated into it. The citation is rather long for this one, but I'd like to turn over the presentation to Sybil Seitzinger, and but first, just a word on Richard. Richard Eppley will be presenting a talk on this, giving background on the paper. And just to give a little background on Richard first, he got his PhD in 1957 from Stanford, and then took a position at the University of Southern California for 3 years, and then worked at Northrop Corporation growing phytoplankton for spaceships, or algae for spaceships for 3 years, and then was at Scripps from 1963 to 1990, at which point he retired. And I said, well, what have you been doing since then? And the answer was having fun. Having fun includes travel, golf, dancing, restaurants, and just having a great time. And we're just delighted, Richard, that you come to be with us today to talk about this wonderful paper that many of us have enjoyed over the years. And Sybil, if you could, and Richard, could you come up to the front? Thank you.
So I'm honored to present this award on behalf of ASLO, and it reads the John Martin Award for a high impact paper in the aquatic sciences, presented to Richard Eppley and Bruce Peterson for the benchmark paper, Eppley and Peterson, Particulate Organic Matter Flux and Planktonic New Production in the Deep Ocean, published in Nature in 1979, providing the first estimate of global new production and showing how the ratio of new to total production varies with depth and proximity to land. Congratulations.
Thank you very much.
Thank you for this loud.
Okay.
Is my mic on? Very good. Well, we go from the young and pardon me, this is very humorous to me. We go from the young and fresh to the old and worn. And this paper was, as you can see, 1979. How do you do this? There we go, 1979. Which is now 30 years ago, when Bruce and I were struggling with this monster. It almost wasn't published because lots of people thought it was trivial, and others of my colleagues at Scripps didn't believe it, and so forth. So somehow it worked its way out and became a bestseller after all. My children have been proud of me for some time because they have the audacity to look at the Science Citation Index from time to time. There's a picture of the paper, my only paper in Nature, so of course I'm very proud of it, and Bruce is too. He sends his regrets. However, he's doing something productive. There he is. He's working on fresh water flowing off of the Arctic and the subarctic into the Atlantic Ocean and wonderful things like that. This is a picture of the food chain group at Scripps where I worked for many years. And I thought that I would point out some of the characters in this picture because it's kind of a who's who of biological oceanography in the time. I think I can see him from here. This is me. And that's Osmond Holm Hansen. Rocky Booth, who built the apparatus to measure the ozone hole in the Antarctic using land-based UV monitors. Peter M. Williams, who had a career in DOM studies. Farouk Azam, who's already been here for this award, I guess. Angelo Carlucci. This is Tony Koslow, who after many years being away is now back at Scripps. This is Rob Olson, who is at Woods Hole, many of you know. This is John Cullen when he was a student. Let's see, this is Jim Ammerman, who won the Young Investigators Award way back when. Who else do I see? George Jackson. And look at this one. This is Jed Furman. I thought you'd enjoy that. And this is Jack Beers, who worked on microzooplankton when he was in the food chain group at Scripps. Is now retired to the desert. I think that's most of the scientists whose names have been on papers. I would like to point out the Frida Reed, who identified phytoplankton for us for a long time, and Doris Osborne, our secretary, Dennis Long, who looked after getting the ships loaded and that sort of thing, Betsy Stewart, our programmer, and so forth. Could go on and on, but I won't. Anyway, it was a very fun group to be with. There are a few people missing from the picture, like Mike Mullen, who was a zooplankton guru, Ed Ringer, and a few others. Well, this was the Gehring and Dugdale productive system for the surface oceans. And the concept of new production and regenerated production came from this basic diagram. And the idea is that new production is from allochthonous inputs to the photic zone, whether it be a nitrate from depth or N2 from the atmosphere. And of course, we didn't have any measurements of nitrogen fixation to speak of in those days. And the other was regenerated production, which is the recycling within the euphotic zone, which at the time we thought was primarily due to ammonium. But Jim McCarthy did his thesis on urea and showed that urea was an important component of regenerated production. We never had much luck trying to determine the role of amino acids and other organic nitrogen. But the idea was that new production would drive the export of the sinking particulate organic matter, plus the fish catch, and other nice things you can think of. The question was, what could you do with this concept? And ultimately, I'll get to it. There was beginning to be a fair number of new production measurements where, starting with Dugdale and Gehring, they would measure the tracer flux of N15 labeled nitrate and N15 labeled ammonium in separate bottles into phytoplankton samples taken out of the ocean. And they were treated just like ordinary C14 productivity experiments, put in devices that attenuated seawater to reflect the depth where the samples were taken, and usually there were 4, 5, or 6 depths sampled. These numbers, 1 through 6, different regions of the ocean, and most of the data are actually Dugdale and Gehring's, except that number 1 is all food chain group stuff from the central North Pacific, where new production was only about 5% of the total. And point number 3 is data from the Southern California Bight, from lots of cruises in the 70s and onward. The other points, 2, 4, 5, and 6, are respectively the Eastern Mediterranean, the Eastern Tropical Pacific, number 4, number 5, the Costa Rica Dome, and number 6, the Peru upwelling. And those are all from a review article by Dugdale in 1976. We had the audacity, at least I did, to draw a line among those points by eye, no statistics, just a steer line. And we used that initial slope to calculate what new production would be where we only knew what the total C14 productivity was, and that's what this axis represents. These are averages of whole cruises, so they're probably, I don't know, 30, 40, 50 points. If you look at individual stations in the Southern California Bight, here are some from 3 different cruises. The different symbols represent different cruises. The line is the line from the previous graph. You can see there's quite a lot of scatter. So you're not going to bet very much money on the precision of these measurements. However, undaunted, I hope you can read some of this. We went to the literature, and there were 2 compendia on C14 productivity, primary production data from the world's oceans. And this first one is from Koblenz-Mischke, and her colleagues Volkovinsky and Kabanova, 1970. And they divided the ocean into different regions, as you see. I can't read it until I get clear over here. This says oligotrophic waters and central parts of the subtropic hylostatic areas. Transitional waters between subtropical and subpolar zones. The extremity of the area of equatorial divergences. And here's the water of equatorial divergences and oceanic regions of subpolar zones. And the neritic waters we didn't include in our calculation, where the parenthesis is, we didn't use that because we could have ammonia and nitrate and any other thing that would be assimilated by phytoplankton coming off the bottom, because these stations would be in contact with the bottom. Anyway, we've got a grand total here. I don't know if you can tell how we did this, but if this is the productivity in grams carbon per meter squared per year, and the percent new production that we pulled off that graph, simply multiplied the two, come up with new production in gigatons of carbon per year. I never heard that term gigaton used until I was at Scripps, where people began to think in terms of 10 to the 9th tons. It was interesting how many people said gigatons and how many said gigatons, and I never knew which was correct. Here's the other one. This compendium is by ocean. It's a little more obvious, and it's from a compendium by Trevor Platt and Subarao, 1975. And once again, the values in parentheses, like for the Arctic and for the Antarctic, we left out because we didn't know what to do with them, basically. But if you add up new production from the Indian, the Atlantic, and the Pacific, you come up with a total of 4.7 gigatons. Did I say gigatons? What was kind of fun to think about such large numbers as that. At the time, Wally Broker had produced an article just the year before, in which he estimated what the oceanic sinking flux contributed to the world's carbon budget, and he estimated that about 10% of the productivity of the ocean probably sank into the deep sea. And you can see that our numbers are, I don't know, sort of comparing 4.7 with 23.7, and the previous one, I don't know how you go back. There you go back. 3.4 and something less than 19.1. Anyway, our numbers averaged about 20% of the primary production would be contributed to the Central Ocean. Well, one of the fun things we could do with this, let me go back one. If you do your algebra with the F ratio, which is the nitrate uptake divided by the sum of nitrate and ammonium and urea uptake, you get this F value that we've been using. And if you take 1 minus F divided by F, you get a number that's represents the number of times a nutrient element is recycled in the photic zone before it sinks out in particulate form. I thought that was really neat, because if playing with the numbers that I had for the Central Pacific, for example, a nitrogen atom would be recycled, according to our number, about 19 times before it would sink out. And in parts of the Peruvian upwelling, let me go back. Go to point number 6, when you see that new production is 50% of the total, that would imply that much of the production sank out as intact phytoplankton or undigested fecal pellets, because if you calculate the 1 minus F over F, the left hand, the ordinate being the F, this F ratio, get 1. So it's very quick processing. I wonder if that's really true. The sediment traps would show chains of diatoms in those studies on fecal pellets. Anyway, there are lots and lots of questions that arose from this kind of simple calculations. And I'm surprised that people were so nice for so long. But Hugh Ducklow, who's now at the MBL, said that this relationship, which relationship? This one, provided an explicit link between remotely sensed primary production rates and the ocean carbon cycle. If total production could be estimated from remotely sensed properties, one could apply the algorithm and calculate the export rates as a function of time and space. The F ratio thus provided both a means to define the efficiency of the biological pump quantitatively and a step toward quantifying the function of the pump on a global scale. And he said he would send some slides, but he never did. On the downside, we've just heard about nitrification. And this new production concept ignored nitrification. we had no data. And at the time, Rob Olson was doing his thesis, and he was getting inhibition by light of nitrification in the photic zone in the water off Scripps. So we weren't too concerned about that. But evidently we should be. You've just seen our society award a prize to somebody measuring nitrification. There's another new paper just this last year by Andrew Ewell and co-authors, in which he calculates revised new production in the light of their armchair studies of nitrification. And also, interestingly, there's a new paper just in March in Science by several authors, including Bob Deuce and Peter Liss, geochemists that I've known for some time. And they have studied the deposition, I should say, of nitrogen from the atmosphere, and have concluded that it's a significant flux. And I'll leave you with going to their paper. It's at the March 16th issue of Science to find out about that. Sorry, May 16th. It says it was a culmination of a project involving about 30 researchers from the UK, the US, Germany, Italy, China, the Netherlands, Switzerland, Canada, and Chile. So I feel a little naked up here and face that crowd. And then here are a couple of references that are fairly kind in their treatment of this paper and the concept of F ratio and the use of the figure. It was handy in the development of the Jagoff's project, if only conceptually. However, in this second paper by Laws, Falkowski, Walker-Smith, Ducklow, and Jim McCarthy, they point out that to them it's still somewhat useful. To me, I'm not quite so sure. But in any case, it's very nice to have been the author of a paper that was so widely cited that it became controversial, and that you could kick it or you could not kick it, and there wasn't much you could do by making improvements, except to find something better to do. With that, I'll turn it off, and it's coffee time, I think. Thank you very much.